as we segue out of the midterm into the second half of the semester, I want to point out that everything we've learned so far is now your foundation. So structure and bonding, you've got to have it mastered now. You've got to know how to draw in bond line. You've got to know how to interpret bond line. Electron arrow pushing. We're going to lean into it a lot more, but how do electron arrows tell you how your structure and how your bonding is changing? We're going to do a lot more with acid-base stuff, but also nucleophiles and electrophiles. Stereochemistry and regiochemistry. You have to be good at identifying your functional groups. You've got to be good at distinguishing regiochemistry, like primary carbons, secondary, tertiary, versus like primary alkyl halide, secondary alcohol. Being able to apply that regiochemistry is important. Stereochemistry, like cis and trans. We're going to add some more words into there, like syn and anti. We will still be doing conformational rotations so that we can understand what's happening to a molecule before, during, and after a chemical reaction. Chirality. How does the chirality of the product formed in organic synthesis impact the nature of the product? But the rest of the semester is reactions. A lot of reactions. So earlier you guys asked, how do you master functional groups? And a lot of you agreed flashcards is a great way to practice them. I would say the same thing now about these organic reactions. We're going to go through more than 20 different organic reactions.
Today?
No. Between now and the end of the semester.
Okay.
I actually don't have a good number. 20 might be on the low. 20 would definitely be a low estimate. 50, I think, is a high estimate. So probably, maybe more like 30 reactions. And you will need to be able to distinguish between what functional groups they react on, what functional groups they form, their regiochemistry, their stereochemistry, identifying chirality before and after an organic reaction, and for a selection of those 30 or so reactions, we're going to do mechanisms, meaning how exactly does the reaction occur. I thought of something yesterday. I drove past one of the new city buses, and it said something on it like clean natural gas bus, or clean air natural gas bus, or something. I mean, it was just like above, you know, on the top. They've also got all electric buses now in Salt Lake. Mm-hmm. Those are the gray ones that are driving around. But the older ones that I think have been retrofitted to stop burning gasoline or diesel are burning natural gas. When I typically hear people say it's clean, they mean that it's carbon free. It's not emitting carbon dioxide into the atmosphere. And the reason it's important for us to not put carbon dioxide into the atmosphere is because of infrared absorption. Carbon dioxide absorbs through its CO bonds really well, and it retains all that energy in the atmosphere, transforming it into kinetic energy rather than letting it radiate out. So when it says clean natural gas, to me that feels like an oxymoron. But it is cleaner than burning gasoline. And this would be an example of an organic reaction that we'll never do. So when you burn natural gas, what's the IUPAC name of natural gas? Methane. When you burn natural gas, we react it with oxygen and a little bit of heat or a spark. We produce CO2 and H2O. I want you to notice that this is not how we show a chemical reaction in like Gen Chem. In Gen Chem, we are typically putting reactants on one side of the arrow and then products on the other side. And what I've done is I've put a reactant over the arrow. Organic chemists use the arrow to save space a lot of times. Or they'll use the arrow to highlight what they're starting with that's really of interest. And then the arrow is what they add to the thing of interest to make this conversion. Organic reactions don't always lean into stoichiometry or balancing the coefficients. I will say 90% of organic reactions are 1-to-1-to-1 stoichiometries. They don't usually need coefficients. This one would actually. This one would need a coefficient 2 in front of oxygen and a coefficient 2 in front of water to balance it. But again, an organic reaction doesn't always show you those balanced chemical coefficients. Okay, this is predominantly what happens when you burn methane. There's just that one carbon that has to get oxidized, and there's not a lot of byproducts that are possible. And by byproduct, I mean things that don't go to completion. But when you burn octane, and you are aiming to get 8 equivalences of CO2 and a lot more equivalences of H2O. At this point, I'm just, well, I think it's 16, but I don't care about balancing it. Somewhere along that process, every single one of the carbon-carbon bonds has to be broken, in addition to all of the carbon-hydrogen bonds being broken. The more bonds you need to break to get through to the end of the reaction, the higher the probability that you won't break all of those bonds every single time, which means that there are a lot of possible byproducts. Those byproducts would be char, basically, charred things. For instance, what if I had a reaction where the methyl group of octane was oxidized and broken off, but then the other 7 carbons in the structure maybe weren't broken off, and that one carbon next to the methyl got oxidized perhaps, but not fully combusted. Now you've got this organic byproduct that's being pumped out with the rest of your combustion. Okay, maybe that's not very likely, but what if parts of this molecule get decomposed and other parts of it don't get decomposed, but they still get highly oxidized? These are byproducts of the reaction, minor products in the reaction, but now they're being spewed out as particulate matter. It's not just CO2 that gets wicked away in the wind and dispersed and spread out, but these often sit around and you breathe them in, and they're not good in your lungs and they can do damaging things. When you see semi-trucks, especially when they're like driving uphill and they're powering into lower gear, and then all that black smoke comes out, that black smoke is partially combusted organic compounds and not fully combusted organic compounds. That's the incomplete reaction. That's the byproduct. So I guess by the buses saying it's clean air that's coming out of our exhaust, they mean there's very little chance of this partially oxidized, partially combusted byproducts coming out because they have such a small carbon chain. The larger the carbon chain, the higher the chance of partial combustion. The smaller the carbon chain, the higher chance of complete combustion.
Oh, versus like octane.
Exactly, exactly. Now there's also catalytic converters in your car, and that's because if instead of making CO2, if they instead make CO, which is not as oxidized as CO2, if it instead makes CO, we want to convert that into CO2. Reason being, carbon monoxide binds to the iron in your hemoglobin really well because it actually has a lone pair on both carbon and oxygen. And carbon likes to share lone pairs. Oxygen, not so much. And so the carbon shares its lone pair with the iron really well. Iron actually shares electrons back, breaking one of the pi bonds in carbon monoxide and effectively pulling the carbon monoxide tighter onto the iron. So if you breathe in carbon monoxide, it's hard to get carbon monoxide out. If you breathe in too much carbon monoxide, it's hard to get oxygen where it needs to go because its transportation vessel is locked up with carbon monoxide. Same thing happens with cyanide. So if our cars are doing incomplete combustion, meaning this stuff, which is particulate matter and not great to be breathing in, or this stuff, because it hasn't fully oxidized, we need to try and make sure that we don't breathe in this stuff. So your car has a catalytic converter, meaning the catalyst is not consumed and it can run, it can last for the lifetime of the car, but it will convert carbon monoxide into carbon dioxide by using more oxygen that's in the air. Carbon dioxide won't kill you in the same way that carbon monoxide will. Certainly not in the same levels. Yep. You got a question, Patrick?
I had a question. So, like, going back to the octane, are there like any engines that could like burn it more fully? Or?
High efficiency engines. Yeah. So you rarely ever see soot coming out of a jet engine. That's a high efficiency engine. They need every last bit of power. Also, if you have an incomplete combustion, you're not getting all the energy that you could have out of that molecule. So jets are really good at burning, and you'll notice that the air that comes out is hot because you can see like the wigglies, and it's clear because carbon dioxide and water don't absorb in the visible spectrum, so they come out clear. If you ever see black soot coming out of an engine, it's not burning well. How about in the winters when all of our engines are pumping out white smoke? Is that evidence of incomplete combustion? What is it? Yeah, it's water. Sorry, that was the worst possible timing. It's that hot water vapor that's being produced by combustion that is now being cooled by the cold air and condensing into a little cloud. Do you need some water? Okay. Okay. So this is an example of a reaction you've seen in general chemistry. You probably learned how to balance combustion reactions when you were learning how to do stoichiometry. It's also an example of an organic reaction. It's just not an organic reaction that an organic chemist uses. It's an organic reaction because it uses a hydrocarbon. But it's really not one that's usually of interest to an organic chemist. But taking that perspective, the reactions that you already know are going to look different in organic chemistry. We're going to leverage that arrow in different ways, and we're not going to see a lot of numbers. We're not going to write a lot of coefficients. It's just going to be structures and chemical formulas. All right. I think I actually want to do this. Tell me if I'm using this word wrong. I might be, but I don't know if I care enough. Anatomy of the organic reaction. So the components of the organic reaction. We start with a substrate. Sometimes just referred to as the starting material. Sometimes referred to as a precursor. Substrate, I've had students before tell me, doesn't make sense to them.
Feels like enzyme-y.
When you're in biology, you say the substrate is what helps feed your enzymes. No. A substrate is something that kind of provides the nutrients or whatever.
It's the thing that
Like binds to the enzyme.
yeah.
Binds with it. Maybe in gardening, a substrate is kind of the soil, the medium. In this case, we often refer to the substrate as the thing of interest, the thing we're starting with. Even if you're actually mixing two things together, the substrate is the organic thing that you're starting with, or perhaps the component that has most of the atoms that will end up in your product. Different names for it. Then we have the reaction arrow. And over the reaction arrow, we can put inorganic reagents. We can put solvents. We can put catalysts. And over the reaction arrow, we can put multiple steps. And we differentiate these multiple steps by saying first, second, third, etc. There are some people out there that will say using the top versus the bottom of the arrow is designated for different things, but that is not true worldwide. Commonly, we put the solvent just underneath the reaction arrow, but it doesn't have to be there. Sometimes we write what the catalyst is, and then we put in parentheses how much we're putting. Catalytic amounts. And we just abbreviate it as CAT. The steps that go over the reaction arrow. Sometimes all of the steps can be written above the reaction arrow. Sometimes they can all be written below the reaction arrow, but a lot of times you'll see the first step written on top, and then the subsequent steps written underneath them. The reaction arrow in organic chemistry is just this free-for-all. In fact, because we're often mixing two things together, it doesn't matter what is written over the arrow and what is written before it. Like here, the substrate was the organic thing because we're in an organic chemistry class. But if we were an alien species and we were really interested in how oxygen reacts, we could have written this as, look at what happens when oxygen reacts with methane. There's nothing wrong with swapping what goes over the arrow and what comes before the arrow. It's just usually a matter of preference for what you're focusing on. Reactions in organic chemistry are quite different from reactions in general chemistry. And then, of course, we have the right-hand side. Sometimes we have major products. Sometimes we have minor products. Sometimes we have byproducts. Sometimes minor products are considered byproducts. Sometimes, it depends on your perspective, the same compound might be a major product in one reaction and a byproduct of another reaction. In some reactions, I want to make methanol. In other reactions, methanol is a byproduct of my reaction. So these are just terms that we give. All right. Did I use anatomy correctly? Is that a...
Sure.
Yeah? It's definitely a description. Okay. What I want to do with you now is expose you to a bunch of chemical reactions. So the most of this worksheet is just showing you chemical reactions, especially reactions that you'll see in this class. Some of them are reactions that you'll see in OChem 2. So let's classify our reactions. Are you guys okay with the abbreviation of reaction being RXN? Okay. I used to actually try and differentiate between like a class and a type of reaction, but those two words just mean too similar of the same thing. So these are different ways that you can categorize reactions, and sometimes different categories can overlap in different ways. The first type, the one that we will start doing next week actually, are addition reactions. An addition reaction consumes a pi bond. I'm actually going to say at least one. You can have an addition reaction that consumes more than one pi bond, but addition reactions generally consume pi bonds. To write a generic example of an addition reaction, I'll show an alkene reacting with this reagent AB. And we see that AB adds across the alkene. So an addition reaction. I've added two groups. We can actually show something similar with an alkyne, which is, both of these are examples of reactions that we'll do this semester. In one case, let me show this on the next line so you can all see it. In one case, the alkyne might have just one of its pi bonds consumed. In another case, the alkyne might have both equivalences of its pi bond consumed, but only if you add extra small AB. No, I'm just kidding. The XS that you see stands for excess. Man, that took me so long to understand when I was in OChem 1. My professor's like, yes, and this is an excess. And I'm like, I see that you're saying it's excess, but I don't know what you mean. What does excess mean? It's like how you write the word empty. You can take excess and just write it as excess, or you can take empty and you can write it as MT, right? Anyways, I don't always abbreviate that as excess. I often actually spell out the whole thing. But do you see how a pi bond is a pi bond? And if there's one pi bond, it can be added across. If there's two bonds, they can both be added across. That's the addition reaction. So I want you guys to look at the three addition reactions in front of you, and I want you to identify what are the two things, what are the two groups that are added across the pi bond. Work with each other. I think you should be able to identify the two things in each addition reaction in the next 3 minutes. identifying what groups are added. So here, I'm saying that I'm adding A and B. In this one, what am I adding across the pi bond? Identify what is added.
It only adds two things every time. Where does the extra bromine and the extra hydrogen go? The air?
Oh, can we? No, yeah, it's saying as much care about like balancing.
Okay. It just happens. Great. Not like clinical. So we just circle what was added? Okay.
Are you talking about like, aren't we just adding a bromine?
Great. Bromine on one side
Yeah,
and methoxy on the other side.
yeah, is that it?
Mm-hmm.
Oh, okay.
Those are the two things. Yep.
Okay.
What about in the one on the right?
And this one?
Mm-hmm.
You added an alcohol.
I agree. OH. What's the other thing?
Did you add
Yeah, I mean, this bond.
a methyl group? But that's not
Right, but we have to add A and B.
an ethyl group?
Are there any carbons that have been added?
No. Well, yeah.
I would say there's 1, 2, 3, 1, 2, 3, and off of 2 is a methyl, off of 2 is a methyl. So all the carbons are the same.
Yeah.
You spotted that OH, but what else has changed?
There's no longer a double bond.
There's no more double bond, which is evidence of that addition.
Yeah. Is it water?
Actually, it's an equivalence of water. We call this a hydration reaction. But water is H2O. I've added OH. So if I've added an equivalence of water, I must have
Another
an H somewhere.
Okay.
But where?
Off a carbon?
Which one? Because there's a lot of carbons, a lot of hydrogens.
This one?
Let's see. How many hydrogens were there before
None.
at that carbon? Weren't you talking about that carbon?
Oh, yeah. There was two.
There were 2 there before.
And now there's only one.
Really?
We know that we add like two different things that are gonna be added on.
How many hydrogens? How many extra bonds needed to satisfy? So 2 hydrogens, 2 hydrogens.
Okay, so they match.
So that wasn't where the extra hydrogen was added.
Okay.
What about here?
In the middle?
Mm-hmm.
None.
And then in the product?
Oh, there's three, so you need one here.
Yes.
Okay.
So that's where the other one is. Remember, we're adding across 2 carbons, and both carbons get a new group. So this carbon got the OH, and this carbon got a hydrogen. It just wasn't explicitly shown.
Okay.
Good.
I was listening to you go through that, and I was staring at this being like, what? And then halfway through was like,
Good.
Is it like that?
Yeah, but those 2 H's were already there.
They were up here?
They were. Aren't there 2 H's there?
Oh, I guess so.
it's just the alcohol, right?
So if this carbon has added a group, then this carbon must have also added a group.
This one?
Yeah, because that's what our example says on the board, right?
Oh, because then that carbon would be deficient if we didn't add a
If you didn't have that hydrogen, and that hydrogen wasn't there before. So you added an H to one carbon and an OH to the other. You're welcome. You guys find the 2 groups in the first one?
I mean, here it is with the beer and OCH, where it's with the, sorry, so is it just the two groups in the first one?
Bromine and methoxy.
And methoxy.
Perfect. What are the two groups in the second one?
Well, only here like the alcohol gets added to it, and then like as you were saying, like the hydrogens too were just like added into the carbons.
Good. And Kayla, I see you. I think you found the two in the next one as well, right? Yeah. Good. Okay, you guys got it?
I get it's this hydration reaction.
Good. You guys got it? Okay. So in the first one, the substrate is a bicyclic alkene structure. Meaning it's got those two rings and it's got this alkene. We've added an inorganic reagent, elemental bromine, and we've added an organic solvent, methanol. And together, this reaction has added across the pi bond a bromine and a methoxy. And maybe you can see where the bromine came from, elemental bromine, and maybe you can see where the methoxy came from, methanol. But the reagents don't always hint at what the structure is going to look like. In this case, I think it was kind of nice. Somebody asked, where did the other bromine go? It's a byproduct, and it just wasn't shown because it just wasn't relevant. What about the hydrogen from the methanol? A byproduct that just wasn't shown. And so this reaction could have produced a byproduct of HBr, the leftover H and the leftover Br. But it wasn't of interest to the reaction. So unlike in general chemistry, where we show everything that forms, organic chemistry often just implies whatever byproducts must be there and looks past them.
So if you gave us the substrate and the reagents and then said draw the product, how would we know that that's what it looks like?
We're going to go through them.
Okay.
We're going to go through all those 30 reactions I mentioned. We're going to go through them all.
Hydrobromic acid.
Yes, it is. Hydrobromic acid. Okay, in the second one, what two groups were added? The OH on one carbon, the less substituted carbon, and the implied or assumed hydrogen on the tertiary carbon. And this, I think, tripped up most of you. This was the first place that it tripped you up because it was obvious to see that the OH was added. But you forgot about that pesky little assumed hydrogen, right? You forgot that it was there entirely because it just wasn't shown. Organic reactions don't have to explicitly show you everything that added. It still requires that you understand the interpretation of bond lines. So what I would say is, if you're going through a reaction and you don't really see how what two things were added, you should start trying to draw out all your hydrogens.
Is it always two things?
Addition? Yes, unless you do two equivalences and then it kind of looks like four things. Do you know what I mean?
So it's never just, so you would never just add one thing?
Not without leaving the other thing either with excess electrons or deficient electrons. Like you can add one thing and then another in two steps. Yeah. Sometimes both things add at the same time. A lot of times though it's one thing and then the other thing. But the desired product, yeah, it adds two things.
Minimum or maximum? Or just always? Or just always? Like if there's an addition reaction, you know you need to look for two changes.
Yeah, two new groups. And I think what a lot of you missed was you didn't realize both carbons would have one group. A pi bond has to span two atoms, minimum. We can talk about that later. A pi bond has to span two atoms, and so for those two things to add, both atoms need to get a new group, right? And this one, it was quite obvious to you because these just stuck out. You didn't connect that it was both atoms getting a new group. When you finally got to this one, and you were like, I see the OH, but where's the other thing? You weren't looking at the other carbon. Pay attention to both atoms from the original pi bond. and look at both atoms after the pi bond has been added across, both of them will get a new group.
Okay, so it's not that you're necessarily adding two things, but it's that because you're breaking a pi bond, both sides of, both carbons will change.
That's right.
But like the actual thing over the arrow could be
Oh yeah,
anything.
yes. For instance, do you guys see the multi-step in this reaction? 1, 2. It's not just happening in one step. First, we add borane. And where is borane in the final product? There's no boron to be seen. The second step adds hydrogen peroxide, water, and sodium hydroxide. Obviously, this is where the OH is coming from, somehow. But where did the hydrogen come from? Maybe the hydrogen came in the first step. Maybe it came in the second. That's where we'd have to investigate the mechanism. How exactly did bonds form and bonds break to change the alkene into an alcohol? And then we could prove where the hydrogen comes in and where the OH comes in.
If there's a reaction where carbon has left over like a lone pair, would it be shown, or would that be something that you'd figure out?
We don't have to show lone pairs. But when carbon has a lone pair, it also has a negative charge. And we have to show negative charges, except for on the exam, where I made you figure out the formal charges. But I gave you all of the lone pairs because you can't have one, you need one or the other. You can't assume both. Okay, what about in that last addition reaction? What was added? 2 hydrogens, one across each side. And what you see in this reaction is a catalyst called Lindlar's catalyst. We'll go over this later, but I am only going to give this to you as Lindlar's catalyst because the reagents that compose Lindlar's catalyst are so long. Palladium mixed with activated charcoal, that's what the carbon is, calcium carbonate, lead acetate, quinoline. That's just too much to write. So we will abbreviate it as Lindlar's catalyst. And what you know about catalysts is that they are not consumed in a reaction. So the reagent over the arrow says H2, and what we've added across is H2. And so obviously the catalyst is just helping to break molecular hydrogen and attach it to the alkyne to form an alkene. All right. The opposite of addition. I know, it would have been a good name. We call elimination. If I'm not adding groups, I'm eliminating groups. When you eliminate a group, you create a pi bond. You guys remember that pi bonds are degrees of unsaturation? So by doing addition, I am saturating. I must have lacked some saturation because I have places to add groups. Elimination is the opposite. Elimination unsaturates a compound. So here I'm going to say Y and Z on opposite carbons. And through some reaction, Y and Z will be removed. Or, like we saw last time, if I have 2 equivalences of Y and Z, I can remove 2 equivalences of Y and Z, and I can make multiple pi bonds. Students have struggled with this before. They look at this reaction as adding an alkene to the structure, adding an alkyne to the structure. But it's by way of eliminating other things. Right? If I'm adding unsaturation, am I really adding anything? Like I added an empty space in my living room. Oh, you did? You created an empty space from thin air or by removing your couch, right? You eliminated the couch, thus leaving in its wake an empty space. You eliminated 2 groups, leaving in its wake a degree of unsaturation, a pi bond. I know it is counterintuitive, so address it and find a way to make it intuitive. Okay, can you tell me what has been eliminated in this reaction given? Chlorine has been eliminated. And a methyl?
It's just a. No, it's just a.
Y and Z, guys. I can't lose just Y. I have to form a pi bond across 2 atoms. I have to lose something from both atoms.
Cl and a hydrogen.
You feel more, you're saying it more confident than Andrew said it.
I think so.
I think so too.
Yeah, because that bond with
Double
the
bond will be-
carbon, that carbon remains the same. The chloride is removed.
Yep.
Right. And then that hydrogen, excess hydrogen is lost when the double bond is formed, and 2 hydrogen remain.
This is basically the opposite of that addition reaction we did over there that formed the alcohol, where it was hard for some of you guys to recognize that the hydrogen had been added to the tertiary carbon because you just weren't looking for it. You're not used to assuming all of those hydrogens. If it means drawing out all those hydrogens, draw them out. When I was in OChem 2, I was drawing out my assumed hydrogens because I still needed practice with it. I also was not engaged in my OChem 1 class the way that you guys are, so maybe you won't need to draw in your assumed hydrogens by OChem 2, but it's never wrong to draw in assumed hydrogens. So when you look at this, you see the chlorine disappears. That was obvious, but the hydrogen. Now, I actually want to talk about this idea you guys brought up, Elvira, that a methyl group went missing because you saw 3 methyl groups in the starting material, but you only saw 2 methyl groups in the product.
Yeah, but one of them became a pi bond.
Pi bond, and then it became a CH2.
I didn't lose any carbons. But I technically did lose the methyl because now it's not methyl, it's not CH3. So one thing that can help you in spotting changes during chemical reactions is what I call mapping your carbons. And to be honest, you don't need to map carbons, you can map any atom. But what I'm going to do here is map my carbons 1, 2, 3. This is not nomenclature locant numbering, although it can feel like that. It's just mapping. I've put some symbols on the left-hand side, and now I'm going to apply those symbols to the right-hand side to see what atoms have gone through what changes. So here's 1, 2, 3. 1, 2, 3, methyl carbon with a chlorine. Carbon 2 also has a methyl group coming off of it. 1, 2, 3, carbon 2 has a methyl group. Notice how I don't need to number every carbon, but mapping just allows me to figure out where those other carbons are. 2 has a methyl, 2 has a methyl. Carbon 2 lost its chlorine, formed a double bond. Carbon 1 lost its hydrogen, lost its double bond.
I was imagining, I was looking at it, at first I was looking at the chlorine and then the methyl group on the other side and imagining it flipping up.
Yep. The conformational change is weird.
Yeah.
Can be really weird. So that tert butyl chloride structure that's drawn there could have also been drawn like this,
Right.
could have been drawn like this. If it had been drawn like this, seeing the change,
Much more.
a little bit more intuitive because the carbons aren't moving around quite as much, but none of them are wrong. All of them are just different correct ways.
We also assume, and doesn't that make NaCl and H2O?
Great.
So can't we also just assume how, oh gosh, I forgot what term we would use, but just like what the products would be? We could assume how they would bond. Like Na would bond as an ion to Cl, and we have OH, losing ion, so we have H2O.
I think you're making an assumption
Right.
because sodium chloride is so common. What you've assumed is that sodium hydroxide is a reagent, an inorganic reagent, but you're assuming it's a reagent and not a catalyst. Because what if it formed HCl? We saw that earlier where this had a byproduct of HBr. What if this had formed HCl? It could have, but if it did, sodium hydroxide would have had to be a catalyst.
That makes sense.
The fact that it does actually form water and sodium chloride as a byproduct. And the fact that it forms those as a byproduct is a result of the mechanism, how the reagents play a role in bond forming and bond breaking. So, and we'll talk about that. We'll talk about the mechanisms. Okay. Now, I've talked about how I can put things onto an organic structure and I can take things off of an organic structure. What other change could I make to an organic structure? A swap. I can put one thing on while taking one thing off, and we call that swap. Oh, no, you're right, swap, substitution. Swap would have been fun, though. Substitution, swaps, two groups. And honestly, I've been saying like at least one, and it's true. Substitution doesn't have to be just one. You can do substitution multiple times on one structure. The example that I have here has the same starting material as, oh, sorry, let me just show this as a generic carbon is bonded to Z, and then carbon is bonded to Y, and then carbon is bonded to Z. By the way, do you know why I'm not using X as like a variable? Yeah, X means halides. We limit X to meaning halogens here. So Y and Z are just kind of ambiguous. And the reason I'm not saying R, I don't want you to think, a lot of times R means carbon chain of some type. It doesn't have to, but that is a very common thing. It's actually very uncommon to substitute carbon groups. So Y and Z are just good variables here. All right, so this example gives us the same starting material and a very similar reagent over the arrow. Instead of sodium hydroxide, we have its conjugate acid, water. And what we see is that sodium hydroxide is running an elimination reaction, but its conjugate acid, water, is running a substitution reaction. So the nature of the reagent plays a role in what change will happen to the structure. And we're going to talk more about what's the difference between hydroxide and water. What's the byproducts in this reaction? HCl. The H from water is lost, and so is the Cl from the alkyl halide. Byproducts in this case, because I don't care that it forms HCl. I might care that it forms HCl because I need to know that it's acidic when it's done, and I don't want to just pour acid all over the place. But that's not what I'm aiming to synthesize. I'm aiming to create the alcohol, and the HCl is a byproduct of that. All right, so those are some of the most common types of reactions. And we are going to learn we're going to go through many examples of each type of those this semester. But there are other ways that we can classify our reactions as well. And these next two can be combined with substitution and elimination and addition in any combination. Oxidation reactions. often abbreviated as O in brackets. And I don't know why. Obviously oxygen, but why the brackets? Not quite sure. Here's how I like to define oxidation, because it doesn't just involve oxygen. This increases bonds to more electronegative atoms. And to do that, you have to remove bonds to things that are less electronegative.
Is that a redox reaction?
Redox is the two parts, yep. But when we talk about organic reactions and oxidation organic reactions, we're focused on the organic structure. And more often than not, we're talking about the carbon being oxidized. So in this example, I give you benzyl alcohol. I'm going to abbreviate that aromatic ring as pH for phenyl for the aromatic ring. And we're providing a reagent that is called pyridinium chlorochromate, or PCC. This is an OCHEM 2 reaction, so these are not reagents or changes that you'll need to know for this semester. But notice how I've increased the number of bonds to oxygen from my carbon. And to do that, I had to decrease the number of bonds to hydrogen. I lost a bond to hydrogen, I gained a bond to oxygen. My carbon has been oxidized.
Would this also be an addition reaction?
Is it addition?
You're creating a pi bond?
Is that the definition of addition?
It's an elimination. You're adding a pi bond.
That's right. It's easy to get them backwards. Good practice. This is an elimination reaction because it creates a pi bond. But no organic chemist would look at this and say, would you mind going into the lab and running this elimination reaction? Because more so than that, it's an oxidation reaction. So it is both an oxidation reaction by doing elimination, but there are addition reactions that do oxidation. In fact, I want you guys to look at the first reaction we did where we added bromine and methoxy. That's an oxidation reaction. Both carbons lost a bond to carbon and substituted that bond for something more electronegative. One carbon bonded to bromine, one carbon bonded to oxygen. So that first reaction we looked at was addition and oxidation. This is elimination and oxidation. The second one adds an alcohol to one carbon, oxidizing it, and adds a hydrogen to the other carbon, reducing it. So that second, that hydration one, that reaction is net neutral. It's oxidizing one carbon, it's reducing the other, so overall the molecule is neither oxidized nor reduced. Now, Gavin, you asked, is this redox? Yes. Specifically, oxidation to the carbon, which means reduction to the PCC.
Will there always be redox?
Redox is two sides of a coin. You can't have one without the other. If electrons are lost, they have to go somewhere. If electrons are gained, they have to come from somewhere. But we focus on what change is happening to the organic structure.
Does that mean we kind of ignore the reduction step? Like we don't ignore the step, we don't even write it out?
We're not writing it out. Yeah, notice how we're not even writing the byproduct of PCC. Pyridinium chlorochromate becomes something else not of interest to any organic chemist, and it will have to get worked up after the reaction is done and washed away, extracted. There's an aspect here where we can talk about oxidation states. I don't talk about oxidation states very often, but they are not hard to calculate. There are different ways to calculate it. But I like to say that the oxidation state is the sum of bonds to less electronegative atoms minus bonds to more electronegative atoms. When a carbon is bonded to something less electronegative, I did it wrong. No, sorry. I just need to flip these. Bonds to more electronegative minus bonds to less electronegative. Sorry. When a carbon is bonded to something less electronegative than itself, carbon takes the electrons, -1 oxidation state. When carbon is bonded to something more electronegative than itself, it loses electrons, +1 oxidation state. When carbon is bonded to carbon, 0. Doesn't factor in. So something more electronegative, positive. Something less electronegative, negative.
Can you do like a very fast example?
Let's do it for this one. The carbon, the benzylic carbon off of the benzene, is bonded. So I'm looking at this guy. It's bonded to oxygen once. And it's bonded to hydrogen twice. And carbon once, which would give it that 0. So this is a +1 for being bonded to oxygen and a -2 for the bonds to hydrogen gives a -1 oxidation state.
And the double bond would be +2 oxygen, right?
Good. Sorry. Here, now we get oxidation state is 2 bonds to oxygen minus 1 bond to hydrogen, a +1 oxidation state. Is that what you said?
Well, yeah, the double CO double bond is a +2.
Right. The CO double bond counts twice.
Yes.
Yep.
We don't count the phenyl ring.
The bond from carbon to carbon has no difference in electronegativity. So there's no pull or push of electrons. Good question.
So it's the oxidation state of carbons. You're only looking at carbons?
True. The oxidation state of hydrogen is almost always +1. Unless hydrogen is bonded to hydrogen, or unless hydrogen is bonded to a metal, like sodium hydride, H-. Otherwise, hydrogen's oxidation state is almost always +1. Oxygen's oxidation state is almost always -2, unless it's elemental oxygen or unless there's a peroxide OO bond. But oxygen is rarely going through a redox change.
Elemental oxygen would be 0.
Mm-hmm.
Conceptually, what is oxidation state telling us? Is like a positive oxidation state mean it was oxidized?
Good question. Oxidation state is very different from formal charge. Where formal charge tells you, is there a deficiency of electrons or an excess of electrons at a specific atom? Oxidation state is telling you when that atom has the electrons that it does it have control over the electrons, negative oxidation state, or does it not have control over the electrons, positive oxidation state?
So is it natural for organic reactions to want to go from a negative oxidation state to
Nope.
a positive one?
Good question. But I would say it's not natural for reactions to go one way or the other. I'm not going to say that there's necessarily a 50-50 split either, but both are very much common. For carbons to be reduced and for carbons to be oxidized, very much common. Happens a lot.
And then the other question, that first oxidation state where you got -1, those two bonds from the less electronegative, is that, you're counting hydrogen, and then are you counting the second hydrogen attached to that, or?
I'm counting both hydrogens connected to the carbon.
Okay.
So this carbon has 1 bond to carbon, doesn't factor in.
Even though only one of the bonds do end up breaking, you're counting both.
Well, I'm determining this carbon's oxidation state
I see. Okay.
in its environment.
Sorry, was it positive oxidation state meant
Well, think about it. Positive oxidation state means all of its neighbors are stealing electrons from it. A negative oxidation state means it is stealing its electrons from its neighbors. So a negative oxidation state, someone in charge of electrons. A positive oxidation state, not in charge of electrons.
Because it's not good to be the thief.
Not good? I don't know. I won't be the judge of that.
Really?
Someone can be the thief.
Stealing isn't good.
What do you mean? Who says oxygen is stealing? It's literally covalently bonded.
You just said it's taking all of the electrons.
Yeah, well, it is pulling them towards it because it's more electronegative.
Some atoms are more equal than others.
So oxygen, the carbon has an octet, right? Carbon has an octet in both forms. Carbon has all 8 electrons that it needs, but how much control over those electrons does carbon have?
So you're saying in the negative oxidation state, it's the one that's deciding about the electrons it has.
It has more control over how those electrons are used. Okay, let's look at our reduction reaction. When we abbreviate reduction, we often put H in brackets. And this means increasing bonds to less electronegative atoms, which don't have to be hydrogens, but carbon's not more electronegative than many other atoms. So often it's adding bonds to hydrogen. In the example that I've given, we have a ketone that is reduced to an alcohol. Would this be considered addition or elimination? Addition. I'm adding across the pi bond. This was a 2-step reaction that it required. But again, nobody would look at this and call it an addition reaction. They're just too familiar looking at it and calling it a reduction reaction. It gives you more information. Some of the other reduction reactions. At the top, when we had that addition reaction, we added 2 hydrogens across an alkyne. We reduced the alkyne to an alkene by increasing bonds to less electronegative atoms. Both carbons of the alkyne had an oxidation state of 0 because they were only bonded to carbon. And in the product, they both have an oxidation state of -1. They've been reduced. They've been given electrons. Their oxidation state has become more negative. More negative oxidation state, reduction. Okay. Some of the other examples. Well, we talked about how the addition of H and OH oxidized one carbon but reduced the other, which means that that reaction had no net change on the molecule. It had specific changes to each carbon, but no net change to the molecule.
So reduction bonds or reduction reactions are positive oxidation states to negatives, and oxidation is negative to positive.
It's not always like starting from negative and becoming positive or starting from positive and becoming negative. So I would say oxidation makes the oxidation state more positive.
Okay.
Reduction makes the oxidation state more negative. Now, most of the reactions that we've been looking at here are intermolecular reactions. Like the interstate, they travel between, or they include more than one thing. That would be like the alkene plus AB is intermolecular. Although the interstate is kind of a bad example. Do you guys know that Hawaii has an interstate? It's called H1. It is an intrastate highway, but it's funded by the federal government, so it is part of the interstate program and paid that way. So intramolecular reactions are changes that happen within a molecule. The examples that I've given show how one carbon in this structure comes back around to bond to a different carbon in this structure. Let me show you the carbons. Well, I'm thinking maybe I drew my structure wrong. I did. If I start at the carbon that's bonded to bromine, and then I map over to the carbon that is the ketone, what I can see is the formation of my ring. Tell me that I'm missing the methyl group from my ring. Good. Carbon 1 has been turned into a nucleophile, a Lewis base. And carbon 1 has attacked carbon 2 to do an addition reaction. It's added across the pi bond of the CO double bond. I decided to map it how I wanted to map it. You don't have to map.
It's not IUPAC.
This is not IUPAC nomenclature. But I do want you to know that that bond line structure is a wobbly little guy.
Right, so
It spins around. This is one conformation of the starting material, but we know that molecules can exist in multiple different conformations. And another conformation of this molecule looks like this, where you can see that carbon 1 and carbon 2 are a lot closer together. And remember that these are magnets, partial negative magnets and partial positive magnets. So when they are swinging around and a partial negative magnet finds a partial positive, they'll just click together. I've mapped this based on where the bond formation is happening, not mapping this by IUPAC nomenclature. But I do want to point out again, carbon 2 has a methyl group, carbon 2 has a methyl group. Carbon 2 has a bond to oxygen, carbon 2 has that bond to oxygen. So the mapping still makes sense of what changes we're seeing. Look at the next reaction. This has both an alkene and an alcohol in the structure. Then, when reacted with elemental bromine, we form this 5-membered ether plus a bromine coming off of it. Remember that these are addition. This is an addition reaction. This is an intramolecular addition reaction. So if I call these 1, 2, 3, 4, 5, I'm even going to map the oxygen as atom 6. Oh, hang on, sorry, did I screw up? That's not the structure I gave you, is it?
The next carbon up.
Good. This guy is. I probably could have just moved the oxygen now that I think about it. Yeah? Because it's an addition reaction, I expect 1 and 2 to both have a new group added to them. 1 has had bromine added to it. 2 has had the ether added to it. It just turns out that the ether's oxygen came from the alcohol oxygen that was already in the structure. So this molecule has come around to react with itself, intramolecular.
But hydrogen was also added.
Yeah, no, CH.
Oh, I see.
CH. Actually, a hydrogen was added here. This one I did screw up on. This should be a two-step. First, elemental magnesium, and then acid. But this is an OChem2 reaction. This is a reaction that we'll see later in the semester. Notice how the intramolecular reactions form a ring? Doesn't that make sense? If I take a shoestring and I combine it with another shoestring, I just get a longer shoestring. But if I take a shoestring and I tie it around to itself, I get a circle.
Do they always form rings?
Intramolecular reactions? Mm-hmm. Yeah, can you ever say always? I don't know.
Are rings breaking up into
You can, yeah. We can do ring opening reactions, absolutely. All right, so when we come back, we're going to talk more about terminology next week, types of solvents. We're going to look at how reactions flow before we actually start diving into our chemical reactions and their mechanisms. Have a good weekend. See you guys next week.